simply refers to the original message, and the ciphertext refers to the coded message. Now, the process of coding a message is called encryption. When we crack a message, that's called decryption. One type of method that we can use to code a message is the substitution cipher. In a substitution cipher, we simply replace each letter of plain text with a different letter or symbol to create the ciphertext. Now, today we're going to look at a particular type of substitution cipher known as the linear cipher. This cipher uses a linear function to determine the order of substitution mathematically. So before we can use the linear function f of x equals mx plus b, the first thing we have to do is correspond each letter of the alphabet to a number. So as you see, we corresponded the lowercase, the uppercase, and the question mark. You can technically correspond however many you want, just as long as the entire set has a prime number of elements. So once we've corresponded our letters to numbers, the next thing we're going to do is plug in the number for the corresponding plain text letter into the function for x, and our output will give us the number for our ciphertext. Now, for this to work, we've got to get a number that's an element of this set, so between 0 and 52. If we get a number that's not an element of our set, all we do is take that number, divide it by the total number of elements in the set, which in this case is 53, and take the remainder, which will be a number in our set, 0 through 52. So for instance, if we got a 53, since that's not an element of our original set, we have to divide 53 by the total number of elements in the set, which would give us a remainder of 0. So 53 would correspond to A. And with 54, since that's not an element of our set, we divide it by 53, get a remainder of 1, and that corresponds to B. So as you can see here, we can just place a bar over the number, which simply means that A corresponds to the set of all integers with a remainder of 0. So we can see this a little bit better if we encrypt math as fun using this linear function right here. So the first thing we do is correspond our letters to numbers. Then we take the number and plug it into the linear function for x. But as you can see, a couple of our numbers are not elements of our set 0 through 52. So we just divide those numbers by 53 and take the remainder. And we would refer to that as like 9 modulo 53. And the next step is just to correspond the number back to a letter, and we get our ciphertext. Now when we know the encrypting function, which in this case is f of x equals 3x plus 1, we could decrypt this message by simply working backwards and using the inverse function of this to get back to the plain text. But what would we do if we didn't know the encrypting function? Well, I'm going to look at a few methods that we can use to decrypt any type of substitution cipher where we don't know the original encrypting function. So assuming that you have spaces in between your ciphertext, the first thing you want to do is identify the smallest word. In English, there are only 2 one-letter words, A and I. So if you have a one-letter word in your ciphertext, it's either going to be an A or an I. I also have a list of common 2-letter words here. When we come to 3-letter words, the and are the most frequently used 3-letter words. I have a list of other 3-letter words that are commonly used, but the and are the most common 3-letter words. In addition to identifying the smallest words, we can also use frequency analysis to help us determine the most frequently used letter of ciphertext. Here I have a chart showing the average frequency of all letters in the alphabet. And as you can see, the letter E is the most frequently used. It occurs for 12.7% of all the letters in text. So for instance, if you have a message and you notice this particular letter repeated in your ciphertext, chances are it's not going to be a Q or a Z, because as you can see, Q and Z only account for 0.1% of all the letters in ciphertext. So you would want to guess that it was one of these, like A, E, T, something that has a general higher frequency. We can also use frequency analysis with doubles. The most common pair of doubles used in English is double S's. So let's decrypt this following message using these methods. Well, the first thing we would want to do is identify the smallest word. Right off, we notice we've got a one-letter word represented by the ciphertext B. So somebody help me. What are the only one-letter words in English? A and I, exactly. So we know this B is going to represent either an A or an I. So to determine which it is, we're going to look at the 2 and 3 letter word. Well, right off, we notice this 3-letter word right here that starts with a B. So we know this word starts with a B and I. B or an A or an I, excuse me. So, can you help me again? What's the most common 3-letter word that starts with an A? So we're going to assume that this 3-letter word right here represents the plain text word and. So we're going to go through and replace all of the B, capital O's, and K's with A, N, and D respectively. Then we notice that we have a 3-letter word ending in A-N. And we recall that a common 3-letter word with this ending is can. So we're just going to let this ciphertext H represent the plain text C. So we just go back and replace all of the ciphertext H's with the plain text C. So now let's move on and try to apply frequency analysis. Well, if you notice in this right here, we've got several ciphertext letters that are frequently repeated. The ones that seem to be repeated the most are the C's, the N, the Z, the F. So I count them up, and I find that N is the ciphertext letter used most often. So help me again. What's the most common single letter used in English text?
E.
E. That's right. So we're going to go through and we'll replace all of this ciphertext N with a plain text E. We'll also apply frequency analysis right here. We see the double C. Since the most common pair of double is S's, we're just going to replace all of the ciphertext C with a plain text S. And when we get to this point, really the best thing to do is just try to guess words. So for instance, I noticed this 2-letter word right here, it resembles the word is. So I'm just going to go through and change all of the Z's to I's. Alright, so now why don't you help me try to guess some of these words. Can you guess? What does this word look like? Does it resemble anything?
Sublet.
Yes, sir. So we'll guess that this word is inefficient. Okay? So now, what about this? Do these 2 words look familiar? Be easily. That's it. So we just keep recognizing words, and eventually we get to our totally decrypted message, which reads that encrypting messages by substitution cipher is unsecure and inefficient because substitution ciphers can be easily decrypted, as you have just seen in the last few minutes.
Okay, thanks to all the speakers. And do you have any questions? Yes.
I mean, if you say it's inefficient, I'm just curious. It's only inefficient because, and this is, I'm asking, is it only inefficient because the time spent by you wasn't a lot compared to some normal guy, like, hey, I'm trying to decrypt this, but I can't really figure it out? You knew the avenues to take to decrypt it, whereas a normal person wouldn't? Or is it just overall?
Just overall, I did have a little bit more knowledge, but even somebody that didn't really know, you could figure it out. It would take more time, but like today, we use computer software, and whereas it took us 10 minutes, with computer software it can be done in just a few seconds. So that's what makes it inefficient.
It's not a really question, but maybe my observation. I understood now much better how Sherlock Holmes was such a genius. If he would have to decipher Russian or Chinese, he wouldn't be this efficient.
Yes, sir. Yes, sir.
But there could be also different statistics for those languages.
Yes, it depends on the language. Yeah. Any other questions? Okay, let's thank